Okay, to this work contributed by Dr. Wang Yipu and Hu Jihen and Dr. Fu Yuyun. They're all from my group. And thanks for the Dr. Qilo Ming from State University of New York. And thanks for Dr. Zhang Peng from the National Satellite Meteorological Center of China. And also from thanks to Zhang Yuxiang. He was one of my PhD students. Now he is a postdoctor in Beijing University. And thanks for the supervision from Professor Yi Bogrelho, Professor Osvaldo Valerio, and Dr. Rafael. Okay. Since we are all working on forest science, so I don't need to say too much about the importance of vegetation and atmosphere interaction. The point is the vegetation water plays a key important roles in all of those exchanging process between atmosphere and the vegetation. So the vegetation water content is one of the most important controlling factors of those chemical and biophysical interactions. But the different observation methods may need to confuse the conclusion. For example, there is a topic called Amazon confusion, which is talking about, well, drought, which is most likely will occur with the global warming. The drought in Amazon will make a positive or a negative effect on vegetation photosynthesis. If we look at this equation, we will realize first, on the one hand, drought will lead to less precipitation and less water, which will be make a negative effect. But at the same time, in Amazon, drought will lead to less cloudiness, and this will result in more available photosynthesis active radiation. So this will make a positive effect. Multiple papers were published to support the positive effect, which is drought will enhance vegetation growth, and also a lot of people published to support the negative effect. One of the most funny things that in 2007 on Science, there was a paper to say the Amazon forest will green up during 2005 drought. But 3 years later on GIR, there's a paper published that no green up in 2005 drought. So these two studies are focusing on the same drought event and focus on the same scientific topics. And they are using the same satellite observations from the same instrument, which is MODIS. So what is the reason? The reason is that there are a lot of cloud over Amazon, but the cloud classification between the MODIS products version 4 and version 5 are different. For example, in this case, the version 4 product classified much more cloud than that over the version 5. So because the optical vegetation index is very low over the cloudless sky, if those data are classified by as a vegetation, well, this will lead to a small NDVI. So we can realize that the optical vegetation index, such as NDVI, has a lot of limitations. Of course, NDVI is a very successful vegetation index, and it has a lot of advantages. But here, I just want to raise some limitations also. So the first limitation is the cloud contamination, right? And the second is NDVI is only available at daytime, and it has a very shallow penetration depth into forest, and the signal is easy to saturate in those very dense forests. To overcome these shortcomings, we developed a new microwave-based vegetation index. The microwave is an electromagnetic wave that with much longer wavelengths than visible and infrared. Because the vegetation of the liquid water inside the vegetation has a permanent dipole. So it will, when there is external electronic field added on it, it will rotate the molecule of the water, and vice versa. If the water molecular rotates, it will emit microwave. And the interaction between water molecules and the microwave highly depends on frequencies. For those lower frequency microwave radiation, it can penetrate deeper into the forest. In another word, if we observe the upwelling microwave radiation at the top of canopy at a lower frequency, the more contributions will be made by the lower part of the forest. If we observe the signal at higher frequency, the more contributions will come from the top layer of the canopy. So based on this physical fact, we defined the EDVI vegetation index, which is a normalized difference of emissivity at the two frequencies. And based on a microwave radiation transfer model, it was found the EDVI will increase with vegetation water content. Now, this is the original definition of EDVI, and it was published in 2006. So the advantage of microwave radiation, the microwave vegetation index is that it's insensitive to cloud and aerosol, because microwave can have a good capability of a penetration into cloud. And can somebody emit this? And it's available at day and night time. And microwave has deeper penetration into forest. And it is sensitive to vegetation water content. But for the optical vegetation index, it is sensitive to chlorophyll, right? And microwave has no signal saturation issue. So this is the flow chart of how we can retrieve the EDVI. This is a physical-based retrieval algorithm. The core part is a microwave radiation transfer model, which will do the forward modeling of how the microwave radiation will transfer through the forest layer, through the atmosphere, and reach the satellites. And we will combine satellite observation of clouds and to do the cloud correction, so that we can use the microwave radiation observations at the top of the atmosphere to the surface. So using this retrieval algorithm, we can get the land surface emissivity and then calculate the EDVI. So here is a case to show the instantaneous microwave land surface emissivity over China. This was done by using the AQUA AMSR-E measurements. So we observe the time series of EDVI and compare it with NDVI in selected areas in China with different vegetation type. Well, we will realize that the time series of EDVI clearly show the seasonal variation of vegetation. This time series is from 2003 to the later 2010. So each wave represents one growing season, 1 year. So in all selected regions, the time series of EDVI is consistent with NDVI. And in some area, the EDVI are negative, and in some area, the EDVI are positive, depend on the vegetation type. And if we look detailedly, we will find there are some phase shifts between EDVI and NDVI. This is to indicate that the seasonal cycles of vegetation chlorophyll and the vegetation water content are generally synchronous, but with several days shift. For example, we can find that the EDVI drops earlier than NDVI in fall. So after introducing how we can retrieve the EDVI, we can have some applications. The first application is in forest fire study. Since EDVI is an indicator of vegetation moisture, so greater amount of vegetation water will be related to the high value of the EDVI. And this should be naturally related to less probability of fire occurrence, and also related to weaker forest fire test. Is this assumption correct? So let's check it by using multiple satellite observations. So we combine our EDVI retriever with the MODIS retrieved fire counts, and the fire residual power in China. And clearly we find the negative correlation between EDVI and fire count and fire residual power. And since the forest fire are highly controlled by weather also, so we also find that there is a coupling effect that the fire weather index and the EDVI are coupled together to have a controlling effect on both the fire count and the fire radiation power. And we can use EDVI combined with the fire weather index to do some kind of prediction of the fire count and fire radiation power. And we found that if we compare the performance by only using weather index and with using both weather index and the EDVI, we found the performance was highly improved. So this part study will be further will be further discussed by Fu Yuyun literally in today's meeting. Another application is that we can use EDVI to study the volatile organic carbon gas emission. The physics is here, great amount of vegetation water will be related to high value of EDVI, and this will be to show the, in other words, there was less water constraint on the VOC emissions, and this will cause stronger emission. And from the observation side, we should be able to find higher column concentration of associated gas, for example, the formaldehyde. To check this, we also use multiple satellite observations, including the EDVI and the fire count from MODIS and the formaldehyde from OMI, from satellite OMI. So we found generally the formaldehyde the column concentration of formaldehyde is higher over forest area compared to that over savanna area. But this also was highly affected by fire. If we remove the effect of fire, we found higher correlation coefficients between EDVI and the column of formaldehyde. This conclusion is also confirmed in China, and we even can use EDVI into more quantify the emission of VOC. For example, the isoprene. So we used a widely accepted model, which called the model of emission of gases and aerosol from nature, the MEGAN. We use EDVI to do a parameterization of the water constraint factor. So traditionally, this factor was parameterized by soil moisture, and we can use EDVI to replace the soil moisture as a water constraint factor and check the performance in Amazon. And we found, well, we did 3 different simulations with MEGAN and compared to the satellite top-down estimation of isoprene emission, and we found in the very dense Amazon rainforest, because the water is enough, this change doesn't have any effect. But in the savanna area, when the vegetation water content is limited, using EDVI indeed can improve the model simulation, which indicate that we can improve our understanding of the isoprene emission process. So the last application I want to introduce is we can use EDVI to estimate the evapotranspiration rate, because more vegetation water content will be related to stronger physiology activities and more water supply, which will be related to a smaller ET resistance and related to a larger evapotranspiration rate. So we set up a physical model based on surface energy balance and using Palmer equation. And the key point is that we can use EDVI to parameterize the resistance of ET and the stress function in the ET process. And we use the in-situ measurements from 20 sites of Asian flux network as a basic database for developing this algorithm and for the validation. And all inputs in this algorithm are independent from in-situ measurements. So this method is not only can be used in sites, but also can be used in regional and global scale. So, so this is the comparison with in-situ measurements of ET and with the MODIS-ET. For example, here we show the time series of ET. The red dots is from our results, and the black dots is from the in-situ measurements. These are all instantaneous retrieval, and this is the scatter plot in the sites between our EDVI-based ET and the in-situ measurements of ET. And this is the comparison between our results and the MODIS retrieved ET. And also, one of the biggest advantages of our method is that the EDVI-based ET method can be used in both clear sky condition and cloudy sky condition due to the penetration capability of a microwave. But for MODIS-ET, actually, it's only available as a clear sky. So we studied the performance of our method and the cloudy sky and compared it with MODIS-ET. We found that there are our method shows stable performance and the different cloud coverage, and the mean bias of our ET is smaller than MODIS-ET. And also, as I said, the method is not limited at the particular site. It's so easy to extend it to a regional level or in the global level. So this is to show the EDVI-based ET in a selected East Asia region, and we found if we compare the results with the MODIS-ET, we found generally they show consistent temporal and spatial distributions, and the annual mean difference between them is less than 1.5 millimeters per day. So as a summary, so this is the EDVI study in our lab. In 2006, the EDVI original definition was established in half of forest sites. And then we use it to develop the original EDVI-based ET algorithm. And in 2010, we extended the site-based EDVI to a regional scale in Amazon. And we studied the dynamic response of EDVI precipitation in 2013. And then we retrieved the EDVI and studied the spatial and the temporal features of EDVI in China. And we, in 2020, then we studied the relationship between EDVI and VOC emission. And then we studied this relationship between EDVI and the vertical structure of vegetation. And from 2019 to 2020, we developed 3 sources EDVI-based ET algorithm, and we are still working on to improve the EDVI retrieving algorithm. And the relationship between EDVI and the forest fire was studied, was published in just published in ISPRS. And recently, Dr. Wang developed a method to estimate the gross primary productivity, and he also will introduce this study in the coming meeting. So thanks for listening, and welcome to our lab. Thank you.